Starting with section 4.3, module 4.3, we're now getting into graphing reciprocal and rational functions. Like we talked about before, rational functions are simply fractions that involve variables. So in this section, you will be able to determine the vertical asymptotes and the point of discontinuity for the graphs of rational functions and graph rational functions. This is section 9-3 in your textbook, and in the skill packet that I gave you, that would be sections 8.3 and 8.4. That'll give you lots of graphing practice, and of course we will practice in class as well. So, a rational function is an equation of the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x does not equal 0. You need to think about why we have it there. Q of x equaling 0 on the bottom would give us an undefined function. Cannot have a function where we have 0 as the denominator. So that's kind of a key thing we've got going on. Rational functions may have breaks in continuity, which means the graphs may have holes, points of discontinuity. So if something's not continuous, it discontinues. Or asymptotes in them. Remember, asymptotes are imaginary lines. They're really imaginary lines, but they actually are a limit of where that graph can go. Okay? So an asymptote is just exactly what we just said. An asymptote is a line that the graph of a function approaches but never crosses or touches. So we've had other, if we think about our logarithmic functions and our exponential functions, we've had plenty that did not, for example, did not approach 0. They would get smaller and smaller and smaller and cruise all the way across the x-axis but never touch it. And if you could zoom in super small, you would see that that line actually gets very, very, very close to the x-axis but never touches it. So we're going to find those asymptotes wherever there is a 0, whatever number would make a 0 apparent in the denominator. So, for example, in this, find asymptotes and or points of discontinuity. So, normally an asymptote is going to happen wherever one of these points becomes 0. So if I asked you to find the zeros of these, you would have x equals -2 and x equals 1. Okay? However, binomials that cancel in the denominator create holes, while binomials that do not cancel create asymptotes. So for this, since we have x plus 2 on the top and on the bottom, those in fact cancel each other out. So at x equals -2, we would say that we have a point of discontinuity, which means when we graph our line, it will actually look like this and have a hole and then keep going. Okay? For this, since even with canceling that out, we still have x minus 1 on the bottom. If I plug in 1 here, 1 minus 1 would equal 0. That gives me a 0 on the bottom, which is undefined. So we would have an asymptote at x equals 1. That means when we graph that, we would have this imaginary line at 1 that our graph would approach, but it would never cross over. Okay? So the key to all of these is you must factor to see where your asymptotes and or holes are going to be. Not every graph has a hole. Most rational, I would say all rational expression functions do have an asymptote. Okay, some are vertical, some are horizontal, sometimes they have both. It just depends. Okay, so find any asymptotes and or point of discontinuity. So what you're going to want to do here is factor this first. So go ahead and do that, factor the top and the bottom, before you can determine what is a hole or an asymptote, and you would need to factor both of those. So on the top, you should have gotten x plus 1, x minus 1, that's a special case polynomial, and on the bottom you should have gotten x minus 5 and x minus 1. Now you need to ask yourself if one cancels. Okay, does anything cancel? Yes, x minus 1, which is equivalent to x equals 1. It's a solution of x equals 1 when the factor is x minus 1. They're always the opposite. So that is going to be our point of discontinuity, is at x equals 1. Our asymptote is going to be the other binomial in the denominator and wherever that would be set equal to 0. So our asymptote would be at x equals 5. Okay, so remember, if they cancel out, it creates a hole. If it does not cancel out, whatever is on the bottom, that factor, change it into the solution, and that is where our asymptote is going to be. Okay? Okay, so with rational functions, I do actually find it easier to make a table of values. Once we figured out where the asymptote is, I think it's much easier to just use a table of values to graph. So for this one, the first one, determine if there's any holes or asymptotes. So in this case, we would only have an asymptote. We don't have a factor that cancels on the top and the bottom. So we would have an asymptote at x equals 2. If I plug a 2 into the bottom here, 2 minus 2 is 0. That is where our function is undefined. So we would have an asymptote. And sometimes it helps to do it in highlighter, something that you can see pretty easily. So our asymptote is going to be at 2. So our graph is going to approach that line but never touch it. Okay? So now that I know that, now I'm going to pick 3 values on either side of that asymptote. So to plug into my equation. So I've got 1, 0, and negative 1. And I've got my asymptotes at 2, so I'm going to go 3, 4, and 5. And then I'm just going to plug in here. Now sometimes I like T-charts to kind of have a space in the middle where you actually can do your mathematical calculations. I sometimes find that easier. You certainly don't have to do that, whatever you need to do. So this would give me 1 over 1 minus 2. 1 minus 2 is negative 1. So that would give me y value of negative 1. 0 over 0 minus 2 will be 0 over negative 2. 0 over divided by anything is 0. Negative 1 over negative 1 minus 2. Negative over negative would be a positive. 1. Negative 1 minus 2 is 3. So that would give me 1/3. So let's just graph those points and kind of see what kind of bend we're getting here. So we have 1, negative 1, 0, 0, and negative 1, 1/3. So part of my line is curving, and it's going to curve all the way along that asymptote, but never actually touch it. Okay? Remember what our mother graph of the rational functions look like. So let's plug in here. 3 over 3 minus 2. 3 minus 2 is 1. 3 divided by 1 is 3. 4 over 4 minus 2 will give us 4 over 2. 4 divided by 2 is 2. 5 over 5 minus 2 would be 5/3. So that's 1 and a little bit. So now if we graph those points, we have 1, 2, 3, 1, 2, 3. 4, 2, and 5, and up a little bit like that. So it's reflecting like that. Okay? This should be a little bit more curved, not so diagonal. Okay? So our graph approaches along both sides of that asymptote, but never actually touches the asymptote. Okay? Okay, so I'd like you to go ahead and try practice number 2, and then come back and check your graph and see how you did. So again, I know that I do not have a hole in this particular graph because I don't have a factor that cancels out, but I do have an asymptote. So my asymptote is going to be at, and it's going to be a vertical asymptote again, asymptote at x equals negative 2. So let's go ahead and put in our vertical asymptote. You can do this with a highlighter, you can do it with a thick pen, you can of course do it with your pencil. I just like to be able to see it really clearly there. So that asymptote is going to be at negative 2. So now I'm going to use 3 points to the left and right. So I'm going to use, actually I'm going to give myself room to work out my math again. So x minus 1 over x plus 2, and I'm going to use, so we're at negative 2, negative 3, negative 4, negative 5, and negative 1, 0, and 1. Okay, and I'm just going to go in one by one, so I have negative 3 minus 1 over negative 3 plus 2 gives me negative 4 and negative 1, so that gives me an answer of 4. And you're just going to continue on with all of these like that. Finally, the last one, 1 minus 1, I already know that that's going to be a 0. My answer is going to be a 0 here. 1 plus 2, because 0 divided by anything is 0. So let's go ahead and graph our points. We have negative 3, 1, 2, 3, 4, negative 4, and 5 halves. 1, 2, 3, 4, 1, 5 halves is 2 and a half, just like that, and negative 5, 2. So our graph is coming like this. And then we have negative 1, negative 2, 0, negative a half, and then 1, 0. So our graph is going to come like that. Okay. So far, so good. No real problems. Okay. Now we go down to number 3, you notice that those polynomials look a little bit more complicated. So the first thing we're going to do is we're going to need to factor the top and bottom to see if we have any factors that canceling out. Now you guys are going to see why factoring is so important, and for you to be able to do it pretty quickly is really helpful when you get to this stage of math class. So x squared minus 9 factors out to x plus 3 and x minus 3. X squared plus 6x plus 9 is a perfect square trinomial, which factors out to x plus 3 and x plus 3. Now I've got a factor that cancels. So I do have a hole, or a point of discontinuity, hole at x equals negative 3, which means wherever my function crosses this line here at negative 3 is where I'm going to have a hole in that graph. Okay? So now we need to determine where my asymptote is. So I've got both in this graph. Because I've got a factor that cancels, I have a hole. Because I still have another factor there, that is going to be my asymptote. So I have, in this case, it just happens to be in the same place. Happens to be at, the asymptote is also at x equals negative 3. So now I'm going to go ahead and I can actually, once these are canceled out, I can use this only for my calculation of what I'm figuring out. Keep doing that. Give myself room to do my work there. Okay. And because I'm running a little bit out of room at the bottom of the page, I'm going to go like this. Okay, so I'm figuring out x minus 3 over x plus 3. X minus 3 over x plus 3. I know now that my asymptote is going to be at x equals negative 3. 1, 2, 3. Okay, so I'm going to pick points of negative 4, negative 5, negative 6, and then negative 2, negative 1, and 0. Okay, so I'm going to go ahead and fill these in. Put you on pause for a minute while I do that, and you can come back and see my results. So I've got my 2 tables filled in now. And remember that I had one table, I just ran out of room, so I just split it into both sides of my asymptote. So wherever now, this would have been a hole, but I've got a hole automatically because I know that my line is not going to touch anything on the asymptote. So I have negative 4, 1, 2, 3, 4, 5, 6, 7, negative 5, 1, 2, 3, 4, and negative 6, 3. So it's going to look like that. And then I've got -2, -1, 2, 3, 4, 5, -1, -2, and 0, -1. So you can see the shape that all of these are taking. Okay? Good. So moving along. Let's do one more. Okay. So again, I want you to go ahead and graph this independently, and then you can come back and check your work. Okay, so you should have factored the bottom of that equation and gotten x plus 1 and x minus 1. Then because my x plus 1 factors out, I know that I have a hole wherever that would be created. So that is at x equals -1. My asymptote is the opposite of -1. So my asymptote is going to be at +1. So now I know with that hole, wherever my value is for -1, that's going to be a hole in my graph. So let's figure out where that would be first, and I'll show you how you do the graph for that. So we're going to go to the left of my asymptote, so it would be at 0, -1, -2. And then to the right, I would be at 2, 3, 4. Okay? We have 1 over -1, which would be -1, 1 over -2. This one you didn't really need as much of the room to work, but it's okay. It's kind of, I think it's kind of helpful. And you've got room, so why not use it? Then 1 over. Okay, so right here, I know that my hole is at wherever -1 is. So where this is, that's going to be the hole. I am not going to draw my line through that point. So you're going to have 0, -1. Now at -1, I have 1/2. So that's actually going to be a hole. And you draw it just like that, just like an open circle. You're going to draw the line to that, skip over it, and then start again. I'll show you in just one sec. And then -2, -1/3. So the line is going to look the same way that it has, except that line is not going to go through that point. So I'm going to kind of zoom down a little bit so you can see what happened. So I drew the line up to that hole. I'm not drawing the line through it. It's on the other side of it and then continuing on. That means there is no value for that function at x equals -1 at this point. That's what the hole means. Okay. The other side we have no issue. There's no hole. The other side there is nothing above the x value of 1 that you could put in that would give you an incorrect answer. So everything else there is fine. So we'd have 2, 1, 3, 1/2, and 4, 1/3. And it would look like that. Okay? So that's how to graph. We'll have some more practice in class. And that's it for Module 4.3.